Hey, what's up YouTube? In my last video, I gave Unreal Engine scriptable tools an introduction and I explained how they could be used to paint flow maps in Engine. In today's video, I'm going to dive into a similar, but not quite similar tool. It's a weird Frankenstein thing that, upon completion, eventually led me to give scriptable tools a solid try and see if it was a solid alternative. Let me give you some context. In my humble opinion, creating custom editor tools in Unreal Engine can be a mixed bag. Although it's much easier than it used to be, thanks to the great work from Epic's engineers, I still find the process somewhat clunky. While it gets the job done, I often feel it could be more streamlined and offer more flexibility. That said, I'm continually learning and discovering new things. Recently, I've been quite pleased with the editor tools I've created, which has slowly changed my perspective on the matter. But still, to this day, my preference has always been to build tools directly in-game. To me, this method offers maximum freedom, allowing for custom control schemes, shortcuts, and a tailored interface. However, the main challenge is transferring data from the game back to the editor, which is not Unreal Engine's strong suit. This is why I feel like Epic is pushing hard to expose new features to the editor, such as scriptable tools, utility widgets, asset action scripts, and so on. Anyway, I actually started experimenting with some kind of in-game paint mode a long time ago, long before scriptable tools were a thing in UE. That project, however, remained a half-assed prototype for a couple of years. It's only very recently that I decided to pick it up and finally complete it. I had the feeling that it could be somewhat useful after all. So today I'm going to show what this tool is capable of, how to use it, but also, of course, do a technical breakdown and explain how it works. Sounds good? Well, let's not waste any time and jump right into it. First off, let's acknowledge that this is purely experimental. Curiosity and curiosity alone drove me to see what kind of unique creation I could come up with. Sometimes you discover cool things by accident, and I'm lucky to be in a position where I can experiment with new ideas, no matter how unconventional they might be. So the concept was to create a tool that allows painting 2D grids. These grids would then be baked into textures for GPU access and into data assets for CPU access. The goal was then to have a blueprint function that could read these data assets, enabling CPU sampling of the grids in the same way textures are sampled on the GPU. So first, how does it work from a user's perspective? Step 1, a data asset of type DA_grid must be created. There are 5, but ignore the base one. And if you're wondering, those are custom data assets, okay? Not something that comes with UE by default. So that grid type contains 1 float per cell, 2 floats per cell, 3 and 4. Let's say I want to paint a flow map, so I need 2 floats. Next, a BP_grid actor must be in the scene and configured to specify the desired number of cells and the grid size in centimeters. Please keep the cell count low because it's a blueprint system, so performance is definitely a concern. Next, that's to specify how the grid is painted based on the brush click and drag custom event. More on that later on. For now, let's use the flow one. Then select the data asset you created. By the way, this actor's position is where the grid is going to be located, so you may want to pay attention to that as well. Finally, temporarily switch your level's game mode to that one, and that should be it. Start a Pi session and you should be put in that cool custom paint mode. View controls are similar to most DCC softwares. Middle mouse button to pan the view, scroll wheel to zoom in and out, and hold Alt and click and drag to orbit the view. That paint mode acts like some kind of view overlay, by the way, so you can tweak the overall opacity. Next, there are brush controls, but you may prefer using shortcuts instead. Hold the S key and drag the mouse horizontally to increase the strength. F key for the fall off, and the R key for the radius. And then, well, hold the left mouse button to paint. Once you're satisfied, exit the game and voila! A texture should have been created and its resolution should match the cell count in X and Y. That texture is also now referenced in that data asset, the number of grid cells has been configured, and the grid values are also stored in it. Please don't change any of this, by the way, let the tool handle that data asset. Anyway, you may then start a Pi session again and update the grid. Hold the right mouse button to erase, by the way. Exit and boom, the texture is updated. And this data asset as well, very cool. Now this tool's behavior is going to be somewhat undefined in case you have two grid actors referencing the same data asset. So please don't do that. See, both grids are loaded, but then you paint onto one and it isn't reflected on the other one. Moreover, there's no way to know which one of the two is saved upon exit. Besides that minor limitation, things should just work, I think. Now the resulting texture may then be used in a material like any other texture, right? You might of course want to project it where that grid is located, so you may specify the 2D location that way, then the projection size that way, and center the projection at that location, and voila. Or best, use the material function I provided, so you just have to specify the location and size. And that texture is indeed projected here. Now obviously world space coordinates go on and on, so the texture tiles, but you may tweak the texture sampler settings to change this. Or create a 2D box mask or any other option, up to you. Now that texture specifically could be used as a flow map, right? It's a 16-bit HDR texture, by the way, and what I painted on the grid is stored as is into the texture to keep the tool somewhat simple, meaning a negative flow direction is encoded as a negative number and the range isn't normalized, so there's no remapping to do to use that texture as a flow map. You can then go back into a Pi session and further modify the grid. Now the one thing to keep in mind is that any modification you do to the grid is not applied to the texture yet, so you don't get to see the updated flow in real time. It's only upon exiting the Pi session that the texture is updated, a bit of a bummer. Now the scriptable tools I demonstrated in my last video support this, and I could technically do something similar here, but I didn't. This tool is meant to be some kind of generic paint grid system, not something specifically designed around flow maps, so real-time visualization was not a priority, plus I tried to keep the tool somewhat simple. Now the cool thing with this system is that you can sample that grid on the CPU in blueprints. Keep in mind, however, it's really not that optimized, because blueprints, you know, so don't expect too much out of it, but it works. Just have to create a blueprint, create a variable of type TA_grid_base, make it point to your data asset, drag it here and call that asset's sample grid function. Give the grid an origin and size, let's use the same values I used in that material, and then feed that function the location to sample the grid at. By the way, that function outputs a vector 4 to support all types of grids, right? But obviously if you used an RG grid, only the red and green channels will contain values. So let's visualize that returned value with an unlit emissive material, nothing fancy. Let's drag that actor over that grid and see it samples the correct color. Now again, this was an experiment, an exercise of some sort. I'm not sure what kind of technical problem this system would solve, especially considering blueprint's performance, but I'm just sharing. I thought it was kinda cool, and if that can give you ideas or inspire you to build your own tools to solve your own problems, then I'm happy. Although it's worth noting that Niagara is a great alternative. It can do asynchronous GPU readbacks to sample a texture on the CPU, like I demonstrated in an earlier project. So again, this blueprint sampling technique here is definitely a bit of a weird thing, but I like weird things. So yeah, that's pretty much it regarding the demo. Time to get technical and dive into the blueprints. I'll keep it somewhat high level and not go too deep for once, but hopefully that should be enough for you to make sense of it. Alright, buckle up. Before we dive into specifics about grids or painting implementation, let's cover the basics. With Unreal Engine, handling inputs and managing mouse and keyboard focus can be, well, tricky. Missing even a single obscure checkbox can stop everything from working as expected. So here's a quick rundown of the setup that works for me. I'm using the enhanced input system, so I'm working with several action inputs. Digital actions for single-click actions like paint, erase, and shortcuts for brush radius, fall off, strength, and so on. Axis 2D actions for view controls like orbit and pan. And Axis 1D action for zooming in and out. These actions are listed in an input mapping context where they are bound to keys and buttons. For Axis 2D actions, the necessary modifiers are added to swizzle and negate components as required. Next, I have three principal blueprints: a game mode, a player controller, and a pawn. That input mapping context is added to the player controller in the player controller blueprint, and the show mouse cursor setting is enabled. This setting may seem innocent, but this is not just a display setting. It also impacts how inputs and focus are handled under the hood. Very sneaky. In the game mode, I specify the player controller and pawn blueprints I created. In the pawn blueprint, I added a camera attached to a spring arm component configured to use the control rotation. I also implemented the different input actions like the view controls. That's to pan the view, orbit the view, zoom in and out, and reset the view. Pretty basic. I'm sure there are better ways to make use of the enhanced input system to build complex controls, key combos and whatnot, but whatever. This works for me and it's simple enough. I collapsed these events into a graph and voila. That's step 1. Step 2. In the pawn blueprint, on begin play, I get and catch the pawn's player controller. That's to initialize the camera's rotation, but also to keep that reference around so I can easily get the mouse location in world space at a later date, for instance. Next, I add a widget blueprint to the viewport. Let's see what it's made of. The root is a simple canvas panel. I created one overlay that is stretched horizontally at the bottom of the screen to create the info bar. There's not a lot to it. An image, a background blur, and some horizontal boxes to contain static texts. I also added a vertical box exposed to other blueprints so I can programmatically add and remove texts to it. That's where grids the user is interacting with are listed, basically. I also added an horizontal box to create a toolbar, to list brush and view parameters using sliders. These, by the way, are also exposed to other blueprints so that upon adding that widget to the viewport in the pawn blueprint, I can provide one of these sliders to this set input mode game and UI node. Which slider is focused doesn't really matter, but this node needs a focusable widget to properly work. This option is also turned off, and that's a critical part of this entire setup. That single node configured like so is absolutely necessary to have inputs behave like I expect them to and still have the cursor show at all times. Next, I get that widget's exposed sliders and bind their own selection changed event. I could have done that in the widget instead and forward events to the pawn from that widget blueprint, same but different. I tend to like monolithic architectures and I prefer having one blueprint that does it all, unless there's just too much. So yeah, I try to contain most of the logic in that pawn blueprint. Anyway, these events, as their name implies, let me know when the user interacts with these sliders to change the brush parameters, right? So the brush parameters are saved in global variables and sent to a material parameter collection. That's an easy way to provide the brush parameters to any material and ultimately visualize the brush radius, fall off and strength directly on grids, more on that later on. Same principle for the view overlay opacity, by the way. Notice this post-process component. A cool thing about post-process components is that they are always unbound, so I'm able to very easily render a post-process material over the entire scene. And that's basically the view overlay effect. That simple material gets the view opacity from that material parameter collection and interpolates the scene color with a plain color. Super simple. However, notice I still get to see the grids, so what's going on? That plain color should in theory be displayed on top of everything. Well, yes, but that's not necessarily true for translucent materials. A post-processed material can be drawn before tone mapping, meaning before translucency is rendered. So you get to see translucent materials rendered on top. That's a cool little trick I already explained in my Niagara gbuffer introduction video, but also in my post-processed VFX tutorial. Anyway, that's how I built the view overlay feature. Alright, so at this point, I can modify the brush parameters with these sliders. Cool. But remember, I also implement shortcuts. So the brush parameters may change and thus sliders should be updated accordingly. It's a two-way thing, right? The slider drives the parameter, but the parameter may drive the slider as well. No, that's a bit less straightforward to implement. And again, I'm sure there are many ways to handle this. I'm just sharing my own solution. So when a shortcut is pressed, I hide the mouse cursor, set the input mode to game only, and I cache the cursor's current position. And when that shortcut is released, I undo that, and I reset the cursor's position. That ensures the mouse movement is consumed when a shortcut is pressed. So I can then increase or decrease the brush parameters, depending on the shortcut pressed, and forward the updated value to the slider. And again, when the shortcut is released, I teleport the mouse back to its initial position to cancel the mouse movement, right? Else it may create a very confusing user experience. There's one problem though. Even if the cursor is hidden, moving the mouse to change a brush parameter using a shortcut literally moves the cursor, so you might reach the edge of the screen where movement is no longer possible. The cursor doesn't automatically wrap around the screen, right? So on tick, if the cursor is hidden, I consider it locked. Thus, I constantly set its position so that it stays where it's at. That still, however, allows delta movement to be recorded. And that's how I handled shortcuts. A bit tricky, gotta play around input modes and different hacks, but in the end it works great. And that concludes inputs on the base setup. I can click on widgets, consume mouse movement with shortcuts, the mouse remains visible unless I decide otherwise, and I keep receiving inputs at all times for the view controls. Everything's working, it's quite a solid base to start with. Next step, 2D grids. In a previous video, I covered the basics of working with grids. If you haven't seen it yet and are not familiar with the subject, check it out, because I will be brief here. You might be tempted to think you need a two-dimensional array to work with a two-dimensional grid. Well, no. See, that grid is stored as a one-dimensional array. There just needs to be some kind of mapping to go from 1D to 2D or from 2D to 1D, right? And that's fortunately very simple. You can simply assume each row is stored one after the other in a one-dimensional array. And knowing the 2D grid's width, you can then easily tell, hey, the 11th index in that array is, well, the 12th cell of the first row. Remember, an array is zero-based, so index 0 is the first cell. The 16th index corresponds to the first cell of the second row, the 34th index to the third cell of the third row, and so on and so forth. So to find a cell's row and column from its linear index, you divide the index by the grid's width, floored, for the row, and use the remainder for the column. To do the opposite, to find a cell's linear index from its row and column, you multiply the row index by the grid's width and add the column index. And I'm using that simple principle to identify which cells the brush overlaps with. So first, in the pawn blueprint stick event, if the view isn't being manipulated, I convert the mouse position from screen to world space, giving me its 3D location right in front of the camera. Next, I fetch all existing grid blueprints. Now, you might worry about performance here, but it's not as bad as it seems. This function uses a hash table, making it actually somewhat efficient for retrieving a specific set of actors. Plus, even though this system runs in-game, this is not the game. It's an offline tool, so real-time performance isn't a major concern. Moreover, I simply assumed I wouldn't have hundreds of grids at once in the scene, and I also knew performance wouldn't be great anyway. It's all built-in blueprints, and I do have to tick quite a few things, as you'll soon see. So this node may actually be the least of my concerns. It at least reliably gathers all existing grids every frame. So for each grid actor, I get its location to perform a line-plane intersection test. Picture that grid as an infinite plane. I cast a ray from the cursor's position to find where it intersects this plane, and that intersection point is the brush's position on the grid's plane. But is the brush in the grid at all? Well, instead of testing a square circle intersection, I expand the grid size by the brush's diameter and perform a simpler square point test. So this function tells me if the brush is within that grid based on the grid size, the brush's radius, and the brush's location relative to the grid's center point. This only works with world-aligned grids, but I assumed grids wouldn't be rotated. Anyway, I then build a local array of all grids intersecting the brush, and call the intersected grids update function to forward the brush parameters, delta time, and inputs. More on that in a second. That local array is then copied into a global variable, but before that I compare the two, thanks to sets. That lets me get the grids that are only now intersecting the brush, so I can call their highlight function just once. And similarly, I get the grids that are now no longer intersecting the brush, so I can call their unhighlight function just once as well. Finally, I list the intersected grids in that widget's vertical box. I built a small system that allows me to create a pool of text objects, so resources are created only when needed and recycled, but to be honest, I probably over-engineered this. And considering it's not of utmost importance, I'll skip this. What's important is this. That's how a grid receives a custom tick event when the brush intersects it. At which point, the grid caches the brush parameters it's given, and it also computes the delta values, meaning how much these parameters changed since the last tick. That's mostly relevant for the position though, to paint flow, right? So you can keep track of the brush movement. I also forward the brush's position to this meshed material instance, but ignore this for now. I'll get back to grid visualization later on. For now, let's concentrate on what happens when the brush intersects with the grid. So now that I have the brush's position on the grid's plane, I need to figure out which cells the brush intersects with. First, I get the brush's 2D location relative to the grid's lower corner. That's because the cell at index 0, 0 is in that corner. Thus, I need the 0, 0 position to not be centered on the grid, but at that corner, if that makes sense. So let's assume the grid is at, say, 25 cm in x and y in wall space, is 1000 cm squared, and has 16 cells in x and y. And let's assume the brush 2D position is, say, at 100 cm in x and y in wall space. Relative to the grid's origin, that's 75 cm in x and y. And relative to the grid's lower corner, 575 cm in x and y. That, divided by the cell size in x and y, floored, results in the cell index in x and y. Thus, to get all cells intersecting the brush, I just have to add the brush radius to its 2D position and do the same math. Next, repeat the process, but this time with the brush radius subtracted from the brush's position. Then I loop from that index in x to that one, and for each index in x, I loop from that index in y to that one, and I can build a list of all intersected cells. And that's precisely what I do here. Now that's obviously a conservative method. The intersection is computed based on the brush's bounds, so you may need to further reject cells based on the distance to account for the brush's radius. I didn't, whatever. Next, that's where the 2D to 1D mapping comes into play, right? For each 2D index, I get the cell's linear index, and assuming I have an array of vector 4s, initialized upon begin play to be sized according to the total cell count, Well, that's how I can access the intersected cells value and modify it to paint the grid. So if painting is ongoing, for each intersected cell, I call this update cell function, which turns out is empty. Yep, that blueprint is a base class, and that function is meant to be implemented in child blueprints, because painting a color and painting flow should be applied differently, right? In both cases though, I first get the brush weight for that cell, meaning I get that cell position, do a distance check with the brush position, normalize that distance based on the brush radius, and apply the brush fall-off. That's how much the brush should quote-unquote paint the intersected cell. So then I get the cell's current value, and based on the provided brush mode, brush weight, and delta time, I either replace the existing value with the provided brush color, add to it, or subtract from it. And then the cell is updated. For flow, it's a little bit different. I no longer care about the brush's color, just its delta movement. And again, that's a value computed here. So same but different. And that's how I paint grids. Now that's a very broad overview, because things are technically a little bit more complicated than that. If you paid close attention, all I'm working with in this scene is a BP_grid actor. And turns out that blueprint is actually empty. The logic I just explained is contained in a blueprint called BP_grid_base. So it's a different blueprint, one I never even mentioned. And clearly it doesn't exist in the scene, so where does it come from? When using that paint game mode, on begin play, I loop through all BP_grid blueprints, get the paint class, make sure everything is okay settings wise, and I spawn that blueprint. Using the owner pin, I also give a way for that blueprint to dialog with the barebone grid blueprint and access its variables. You'll see why in a second. So my thinking was the following. The downside of building an in-game tool is that you may need to rely on actors and things that may consequently persist in your quote-unquote normal game. Unless, of course, you get rid of them. But then what if you need to jump back in that paint game mode at a later date, right? Now, I guess you could contain these grids in a level that isn't streamed in unless in that paint game mode or something. I'm sure there are many solutions. My point is, you may have a couple of actors laying around just for that tool, not serving much purpose otherwise, so I wanted them to be as lightweight as possible. Hence why these just contain a couple of variables, 2 vec2s, a soft class reference for the paint class, to specify how that grid should be painted, and a hard reference to the data asset. I assumed that asset would be loaded into memory anyway, but I could have used a soft reference instead, no biggie. So that actor has no logic and no components, it's quite barebone, right? Only when in that paint game mode do I spawn the grid blueprint that handles the painting, and that has a whole lot more to it, variables, components, and so on. Let's do a brief tour of that blueprint, by the way, because I only covered its update grid and update cell functions after all. It has a static mesh component to display a simple plane, scaled to match the grid size. It uses a translucent material to draw a grid with the required number of cells. Shout out to Ben for this great article. Link is in the video description below. The brush's radius, fall-off, and strength parameters are visualized on that grid using a whole bunch of sear masks, and the brush position set in the grid blueprint. I didn't make any effort to optimize any of this, so I won't bore you with the details. That green material cancels the auto exposure and is faded in and out based on the view opacity, the same parameter the post-process material uses to lerp the scene texture with a plain color. There's also an instance static mesh component to instantiate a plane for each cell. And I'm using per instance custom data to provide the material with per cell information. Does the brush intersect with the cell, and the cell's RGBA value. That's accessed in the material with a vertex interpolator to draw the cell's RGB color, basically. When painting flow though, the material used is a bit different. First, the mesh is no longer just a basic plane, but is actually two meshes embedded into one and differentiated using a UV map. That UV map is used as a mask to isolate the world position of the shenanigan on the arrow mesh, so it's stretched and rotated to match the flow direction and speed. I won't bore you with the details, I've made enough videos on world position offset tricks on my YouTube channel at this point. Anyway, that blueprint also has a Niagara particle system, and it actually brings me to another topic. It's one thing to update that array and paint the grid, but it needs to be baked into a texture. And that's where the Niagara component comes into play. It uses a very simple Niagara system. I'm just using a simulation stage to iterate a vector for array. One I send to Niagara in blueprints here. That's the grid cell's values, right? Upon grid initialization, I also create a render target and send it to Niagara as well. Next, that simulation stage simply iterates over the array entries, does the 1D to 2D mapping I explained earlier, and writes the cell's RGBA value into the render target. Next, when I quit the Pi session upon end play, I get the data asset and get its texture pointer. If it points to an already existing texture, I simply override it with that render target. Else, I create a new texture asset. Finally, I also update the data asset array to reflect the cell's values. And that's how the system works in a nutshell. To summarize, in the pawn, I loop through all grids on tick. I forward a custom tick event to grids intersecting the brush with all the brush parameters. The brush position is converted into a 2D cell index, then into a 1D linear index to modify the cell value as required, depending on the brush mode, brush weight, and so on. That array is sent to Niagara to draw that array into a render target. Render target, that is, upon unplay, converted to a static texture. And that array is also simply copied into the data asset. Also, I almost forgot to mention this, upon begin play, I read that data asset to initialize that array. And that's how the grid save and load features are implemented. Now, one thing to note, there's a nasty bug that's been plaguing recent UE versions. Sending arrays to Niagara is kinda broken. I think there's some kind of serialization issue that prevents this from working unless the Niagara asset is at least open once. That means when just starting the project and jumping into the paint mode right away, the grid won't be rendered into a texture because this Niagara asset needs to be first opened. Quite silly, and it's been affecting quite a few of my projects. I'm really hoping for a fix soon. There's one last thing I want to quickly mention, sampling grids in blueprints. That's done using a data asset. So first, I created a primary data asset to contain the grid cell count and texture reference. It also has a function to sample the grid, and it reuses principles I already explained. The sample location is made relative to the grid's lower corner and is floored to get the cell index. Now, sampling likely means there's some kind of interpolation, and I chose to go with a simple linear interpolation. That means, given a sample location and the corresponding cell index, I first need to get the 3 surrounding cells. However, remember I'm working with a linear array, so getting these involves a little bit of gymnastics. For instance, getting the cell above means adding an offset to the linear index equaling the grid's width. Anyway, once I have these 4 cells, I need to know how close the sample location is to these 2 columns and to these 2 rows in a 0 to 1 range. And the fractional part of that position gives me that. So next, the idea is to interpolate these 2 cells, and these 2 as well, and then further interpolate the 2 results along the y-axis. That happens in that function that is empty in the base class, because it is meant to be implemented in child classes. So I've got a child class for grids that contain just 1 float per cell, 2 floats per cell, and so on. And so it's just a matter of interpolating the 4 cell values, float, vector 2, vector, and vector 4, like I explained, and voila. That lets you sample the grid on the CPU, in a very costly manner, yes, because of blueprints, but whatever. Again, I just want to reiterate, this is just an experiment. I'm not sure what technical problems this specific system solves, if it solves any at all, but it was mostly a way for me to show you how you can build custom tools in-game. It's a method that definitely requires some work, but it at least forces you to get your hands dirty and figure out how to work with widgets, inputs, and so on. So it's all in all a great way to learn Unreal Engine. Plus, the user experience you can offer with an in-game tool can often, in my humble opinion, surpass what you can offer with scriptable tools, utility widgets, and so on. The sky's the limit. See, I can pick a color, hold shift, and drag and drop it onto a grid to fill it. That's the nice extra little things you can provide with in-game tools. And turns out it's not even that complex to build. Shout out to the guys on Ben Yui's Discord for the help, by the way. So in that master widget, I placed another user widget. And if I click on it while holding shift, I try to detect a drag. Else, that means I'm selecting a new color. So I need to move that little dot where the cursor is relative to this widget. That position is also clamped based on the widget's local size, so it remains in that area. Still using the widget's local size, that position is also remapped to a 0 to 1 range in both axes to let me compute the selected RGBA color. The x-axis drives the saturation, and the y-axis the brightness. And so, when a drag is detected, I create a small widget to display the dragged color, and I create a drag operation. The next step is a bit counterintuitive. On drop, I just return true. That event means the drag and drop operation ended on the widget, and I don't really care about that. If the drag and drop operation ended outside the widget, the onDrag cancelled event is triggered, and that's what I'm interested in, right? So at that point, I get the mouse position, figure out if there's any grid under the cursor, and if so, I fill that grid with a dragged color. And that function simply replaces the RGBA value stored in all cells. Voila! So yeah, I like building in-game tools. Again, sure, you have to do some work to implement inputs and widgets and whatnot, but it's also a great exercise. And in the near future, I'll be looking to use that method to rework from scratch my EV generator. So stay tuned and subscribe if you don't want to miss that video. Alright, I think that's it for today's video. Files are available as a tier 3 reward on my Patreon. You'll also find a ton of cool UE educational projects, systems and assets. Any support is much appreciated. Speaking of, thanks to all my patrons for the incredible support. And thanks to you for watching. Alright, I'll see you in the next video. Take care of yourself. Bye bye!